A source produces one of four possible symbols. This time, it produces symbol A. The sender can see the result. The receiver knows the four possibilities, but not which one occurred. The sender must identify that symbol using only zeros and ones. Beforehand, they agree on what each bit will distinguish. Every transmitted bit answers one yes or no question, and the message stops when only one symbol remains. The source keeps producing symbols. Symbol A occurs half the time. Symbol B occurs 1/4 of the time. Symbols C and D each occur 1/8 of the time. Over many symbols, shorter paths mean fewer bits cross the channel. So we score a design by its average number of bits per source symbol. Now choose what the first bit should distinguish. Should it split the labels into two pairs, or should it isolate the common symbol A?
I choose two pairs. Either answer leaves two labels, so one more question finishes.
That reasoning is exactly right when all four symbols are equally likely. But test the common symbol A. The pair root spends a second bit. The isolate root stops after one bit. One symbol cannot settle an average, so follow all four. Complete both codes. Splitting two pairs gives every symbol depth 2. Isolating symbol A first, then symbol B, gives depths 1, 2, 3, and 3. Every leaf still names exactly one symbol. Only the number of transmitted bits changes. Weight each depth by how often its symbol occurs. The balanced code averages 2 bits per symbol because every path has depth 2. The other tree gives 1/2 times 1, plus 1/4 times 2, plus 2 copies of 1/8 times 3. That is 7/4, or 1.75 bits per symbol. That is 1 bit saved for every 4 symbols on average.
So balancing labels was fair, but it spent too many bits on the common symbol.
Now label each branch 0 or 1. To reach symbol C, the answers are 1, 1, 0. Written in order, they form the binary word 110. One edge contributes one recorded digit, so word length is tree depth. These 4 words are prefix-free. No complete word is the beginning of another. When the receiver reaches a leaf, the current word is finished. The next symbol starts again at the root, so unequal word lengths need no separators. Why do these depths mirror the probabilities? 1/2 is reached after one equal split. 1/4 takes 2 halvings. 1/8 takes 3.
Each halving adds one yes or no answer.
That is exactly right. Base 2 logarithms count those halvings. 1/2 maps to 1, 1/4 to 2, and 1/8 to 3. For a realized outcome with positive probability, we call this its self-information under the stated source model. The source asks for an average, so we will build it one outcome at a time. Symbol A occurs half the time, and its information value is 1 bit. Symbol B occurs 1/4 of the time, and its information value is 2 bits. Symbol C and symbol D each occur 1/8 of the time, and each has an information value of 3 bits. Add those 4 weighted costs. The result is 7/4, or 1.75 bits per symbol. This source average is called entropy. Here it matches the tree's average because every reached gate halves probability exactly. That exact fit is special, not automatic. Claude Shannon made this average central to a new theory of communication in 1948. That was not his first foundational idea. At age 21, his master's thesis at the Massachusetts Institute of Technology had connected Boolean algebra to relay circuits and helped lay the foundations of digital circuit design. 11 years later, while working at Bell Labs, his paper founded information theory. Entropy gave that theory a precise way to measure a source's average uncertainty. Keep the same 4 symbols, but change one rule. Now each symbol has probability 1/4, which familiar tree is cheaper.
Now I choose the balanced tree. The probabilities are equal, so every symbol deserves the same depth.
That is correct. 2 answers for every symbol averages 2. The old probability-shaped tree now averages 1/4 times 1 plus 2 plus 3 plus 3. That is 9/4, or 2.25. Each symbol also has 2 bits of self-information, so the uniform source has entropy 2 bits per symbol. The answer depends on what you are pricing. One realized symbol has self-information under a model. The source has entropy on average. For our first source, that average was 1.75 bits. For the uniform source, it is 2. Real probabilities do not always land on whole tree depths. Coding sequences is how we begin to share that rounding cost.